212 Lab 6, Magnetic Molasses. The purpose of this lab was to see how a falling magnet induces currents in a conductive tube covered in aluminum, and how those currents slow its motion, and then compare this to the behavior of a computational model. The system was the bar magnet and the tube that it was in, and the surroundings was everything else in the environment. And our results were a experimental falling time of 0.49 seconds and a computational model falling time of 0.341 seconds. Key physics concepts of this lab are Faraday's law of induction, which says that changing magnetic field induces an EMF in the rings, which generates currents which slow the magnet as it falls. Magnetic dipole field, which says that the bar magnet behaves like a magnetic dipole, which changes the flux. Induced current in rings, which says that each cross-section of the tube acts like a conductive ring with its own resistance and current, which creates magnetic fields. Newton's laws say that the magnet's motion is determined by the balance between gravity pulling it down and the magnetic forces pulling it up. And then the Biot-Savart law relates the magnetic field to the current, length, and distance. Some assumptions for this lab are that the bar magnet acts as an ideal magnetic dipole, and that error, resistance, and friction are negligible. And then possible sources of error are inconsistent magnet drop height or tilting of the tube, so it could hit the sides of the tube, inaccurate timing, and it's not a perfect tube or series of rings. So for the procedure of this lab, we identified and marked the magnet's north pole using a magnetometer app. We measured the tube length and diameter. We held the aluminum tube vertically and then dropped the bar magnet into the top opening. We found the entry and exit times of the magnet using video timestamps, and then we repeated the drop 5 times to compute the average fall time. Here were the results of our lab. As you can see, the average fall time was 0.49 seconds. And here are some excerpts from my code. So here are the results of our code. As you can see, we found an estimated time of 0.341 seconds for the magnet. As far as interpreting the simulation, the current colors, red is the clockwise current, but we don't have that in our simulation. Blue is counterclockwise current. Flipping the magnet reverses the induced current directions, but the magnet still falls slowly because Lenz's law always opposes the motion. The simulation time differs from the real 0.49 second time probably due to the assumptions that I mentioned that we made. And possible sources of error. Velocity time plot, the curve rises and then levels off, showing the magnet approaching a terminal-like speed where magnetic drag balances gravity. And then if holes were cut into the tube, it would break the closed conducting loop, so the ring currents of the model would drop to nearly zero, and the simulation would show almost no induced currents and have no magnetic drag.